Okay, one more graph to use our derivatives with to analyze and sketch, and we're going to go with this rational function this time. So there are going to be a couple of features that we're going to want to know right here. First of all, we would want to know what is our domain, and in this case it looks as though we're going to be able to say that our domain is going to be the set of all real numbers except for x equals 2, because that is where we're going to find a vertical asymptote. So x not equal to 2, that makes up our domain. As far as our range goes, well, that's going to be a little bit of a different business, and we're going to have to figure that one out, which we will here once we get through some of our derivative work. I'll point out that this is the kind of rational function where the degree of the numerator is exactly 1 greater than the degree of the denominator. And that was the kind of case where we could use either long or synthetic division to rewrite this function in a way that was a little bit more convenient. So let's do that. Let's use synthetic division. Remember, the way we would set up our synthetic division is that we would put x minus 2 equals 0, so 2 goes on the outside of that synthetic division setup. We're going to have 2, negative 5, and positive 5 as our coefficients inside of our table here. And we're going to just bring down the first number, 2, multiply that by 2, add down the column, negative 5 plus 4 gives us negative 1. Multiply 2 times negative 1, that's going to give us negative 2. Add down the column to give us 3. And this is going to be our remainder. And these two numbers will represent the coefficients of our quotient. So we actually can say that we have the function y equals 2x minus 1 plus 3 over the divisor of x minus 2. That's useful for us in a couple of ways. For one thing, we can say that this is the kind of function where we know that this is going to have, well, we want to be able to find places where this function is going along. We're going to have a slant asymptote. We're going to have a vertical asymptote at x equals 2. We know that x minus 2 does not divide evenly. Horizontal asymptote, well, since the degree of the numerator was greater than the degree of the denominator, there was none. But we could say there's a slant asymptote, and that occurs at the line y equals 2x minus 1. All right, that's good for us. That gives us some idea of where to go. Now, as far as graphing this thing, what we're going to need to do is we're going to want to use the derivative. And I use the derivative of this reduced function because it's a little bit easier to get. The way it'll work out is that you can take your each term by term right here and take our derivative fairly easily. We find, for example, that y prime would be equal to 2 minus 3 divided by the quantity x minus 2 squared. Now, y prime is still undefined at x minus 2, but so is the original function. So that's not going to help us. On the other hand, are there any points where 2 minus 3 over x minus 2 squared is equal to 0? Well, yeah, there sure is, right? I'll show you why. 2 minus 3 over x minus 2 quantity squared. When we set that equal to 0, can be rewritten as 2 equals 3 over the quantity x minus 2 squared. And that can be rewritten as x minus 2 squared is equal to 3 halves. That's 1.5. So by our extracting the square root method, x minus 2 is equal to plus or minus the square root of 3 halves. And there are two places where this maximum, or where critical points at least, we don't know maximums or minimums yet, will be 2 plus or minus the square root of 3 halves. Okay. Now, for the purposes of graphing, if we're looking at the values that we would get right here, the two values are critical numbers. as far as the graphing perspective goes, our x equals approximately positive 0.78 when we take 2 minus the square root of 1.5, and x is approximately 3.22 when we take 2 plus the square root of 1.5. So we're going to have two critical numbers right here. We would want to show where this function was increasing and decreasing, of course, and we could do that by taking these critical numbers and just testing our function. Let's see, if we took a 0. That should be 7.8. What did I say? 7.5. 0.78 here. We could take 2, where we know the function is undefined. This is a vertical asymptote. And then, of course, at 3.22, which is square root of 1.5 to the right of 2, we would want to find out, well, what happens to y prime? And so what we would do is we could just choose numbers, like, let's say, 0. What happens at 0? Well, we get 3 minus 2 minus 3 over 0 minus 2 squared. Well, that's, let's see, 3/4. 2 minus 3/4, that's a positive number. This is increasing. A number that is to the right of 7.8 and less than 2 would be positive 1. Let's check out what happens if we go to 1. That's 2 minus 3 over 1 minus 2 squared. That's a negative number. Okay. We could try a number between 2 and 3.22. We could try 3, as a matter of fact, and we're going to find that's also negative. And then a number to the right of that gives us positive. So we've got this function where we've got a vertical asymptote. It's increasing, and then it's decreasing. There's a vertical asymptote, and it's decreasing again, and then it's increasing. All right. So we know our intervals of increasing and decreasing, but we know that what's going to happen is that this is going to be a relative maximum at this point, because our derivative changes from positive to negative, and our derivative changes from negative to positive here, where we're going to get a relative minimum. So I substituted in my x values right here, and you can verify this for yourself. Substitute in your x values into either your original or rewritten original function, and what's going to happen is that our critical numbers, our relative maximum occurs at the point 0.78 and negative 1.9 rounded for the y value. Our relative minimum occurs at 3.22, and the y value there is about 7.9. Interesting, 7.9. We've got a relative minimum with a value that's greater than the relative maximum. How does that happen? Well, because it's a rational function, all kinds of fun things are possible right here. I know, fun is a relative term. Y double prime, we need to look at our second derivative to check out the concavity for this thing. Our second derivative, if you work this out, is 6 divided by the quantity x minus 2 cubed. Okay, so that means our second derivative is going to have intervals that change, possibly is sign at 2, right, where we have our undefined value here. That's our vertical asymptote. Well, what happens to the left of 2? If we choose a number like 0, we're going to have 6 over 0 minus 2 to the third. That's a negative number, which means it's concave down. If we choose a number to the right, let's say 3, we know that we're going to get 3 minus 2 to the third. 6 over 1 to the third is a positive number, so it's concave up on that interval. 2, however, is not a point of inflection, right? There are no points of inflection. So as far as our second derivative is concerned, there's no point of inflection, which is kind of interesting. However, we have an interval for concave down that goes from negative infinity to 2. And we have an interval that's concave up, which is on the interval from 2 to infinity. Fascinating. Let's take a look and see what that's going to look like. So here we are looking at our information. I've gathered it together. Vertical asymptote at x equals 2. Horizontal asymptote, well, there is none. Slant asymptote at y equals 2x minus 1. Here's a picture where that slant asymptote is. Our domain is all real numbers except for 2. Our range, well, we found those relative minimums and maximums, and when you look at the graph, you'll see why I wrote it this way. We have one y-intercept that's at 0, negative 5 halves. And you can put 0 in here, and you'll see that that's the case. The function's increasing. Let's see. So our function is going to be increasing. We said to about 7.8. Let's illustrate that on our graph right here. We have this function that's going to be increasing to about 0.78. So just a shy of 1 right here. We're going to have this increasing function. Then we said it was going to be decreasing on this interval all the way up to 2. And then from 2 to about 3.22, it's going to be decreasing again. And then it's going to be increasing again. So it's going to be increasing on this interval from 3.22 to infinity. All right. And it's concave. Concavity changes. We have a concave down shape. Our concave down shape goes all the way up to 2. So this is concave down here. And then it becomes concave up here. Concave up. All right, so let's take a look and see how well our function did when we put this in and graph it. Sure enough, there's our picture, this increasing and then decreasing function with a maximum right here. This relative maximum here at the point 0.78, negative 1.9, and our relative minimum to the right of it at the point 3.22 and 7.9, and sure enough, decreasing, then increasing, relative minimum, it's a horizontal tangent, vertical asymptote, slanted asymptote, relative maximum by going from negative infinity concave down to positive from 1 to 2. It's decreasing along that line towards the vertical asymptote. That's a great graph. This is an example of the kind of thing that we can do with these derivatives. Good luck with your graphing.